So for my 140 final project, I decided to make a 4-bit ALU. Now in this ALU I have 8 operations. So the first one was AND. The next one was the OR. And then I had, of course, to round out my bitwise operations, XOR and NOT. And then on the other side of the chip, I had a shift left, which I'll call SHL, a shift right, or SHR, an adder, and a subtractor. Subtract. Let me rewrite that for us. Subtract. So now each of these fed into a multiplexer, a 2-bit multiplexer. Which, of course, all had S0 as the driving signal. So let me finish drawing these in here. And then, so that's S0. And then, of course, they all continued to funnel in. So then the next layer was a mux with S1 as the driving signal, and they all did that. All the first 2 muxes funneled into S1 mux, and these both funneled into my S2 mux. So this looks kind of messy, but oh well. And the output came from the final S2 mux. So now we can see that on this 4-bit ALU, let me move my picture a little bit. I had 8 opcodes, which means I needed 3 bits for the opcodes. And each of these operations, so each operation had 2 sets of 4 bits. Now what that means is, say I have my AND block, I would have A, which is 4 bits wide, and B, which is 4 bits wide, and the output, of course, would be F, which is also 4 bits wide, and that's what makes it a 4-bit ALU. So then, when I was designing this, I realized there's 2 different ways to do it. There's the custom, and then there's the make one piece and replicate it a whole bunch of times. And I chose to do the custom because it's cleaner, but if you have a larger piece than I did, which only had 1,000 transistors or so, you should probably do this the schematic way. So how do you do that? Well, you create your little layout of, say, a NAND gate, A and D, and then say we need a multiplexer. Well, that's 3 NAND gates, and we also need a NOT gate. Now, as you can see, these are a bunch of boxes, which is exactly what you want in the schematic. This allows you to make, say, each box once, and then you just keep placing them. Call that A and B. And so that's how you do it. Now, what did I do? Well, I went and I drew these transistors, and I would keep drawing them pretty much like this. And then the downfall of this is my computer actually started running really slowly as it got bigger. But on the upside, made it so that I was able to make it more compact. So then when I was simulating it, I would have my A's, my B's, and my Q's and my F's. The Q's are the select lines. So let's draw this out. So then I would take some sample cases. So I would say, let's say A is high, and then it goes low for a little bit, and then it comes back high, then it goes low, yada yada. And B does the exact opposite. And we'll say we're doing a adder. So at each point, say here, would be when the output would finally catch up. So I'll just draw these little dashed lines to show when the output would finally resemble. And this is the timing delay that's talked about in most basic logic classes. Okay, so then let's draw this output. 0 plus 1, well that's just a high. Now this is 1 plus 1, so this is always going to be high. Now if we let it all go low all of a sudden over here, where it finally takes hold, you'll see that while it's still at the point here, everything's off, so you would think it would go off, but no, it's going to stay high all the way until it takes effect. Now what this means for my simulations is, on electric, the program that I was using, each transistor adds, or each transistor set or pair adds 10 nanoseconds of delay, regardless of its characteristics. So if, and this is just for switching, if they don't have to switch, they don't add to the delay, of course, which kind of makes sense. But anyways, so each of these goes through, and say I have 5 transistors in a line that switch. Then I would have 50 nanoseconds. So now the problem really becomes, say I switch 5 the first time, and I do the exact same operation, but I only switch 1. Now because even though in the real world you would have to delay for this, the simulator, because it's not very good, showed a switching time of 10 nanoseconds. And normally this would not be true, it would actually be closer to the 50, maybe a couple nanoseconds shorter or longer, but it'd be pretty much the same.